Okay, so we'll start the next session. So after this, there's a photograph. So stick around. Don't vanish. Before lunch, there's a photograph. So we are very happy to have Matt Headrick, who's going to talk about bit threads and holographic monogamy.
All right, thanks. So like the speakers before me, I'll start by thanking the organizers for inviting me to this interesting meeting. This is my third visit so far to ICTS, and it's incredible to see. I think it's the only institute I've visited where every time I come, it looks different and more beautiful. So I can't wait for my next visit. I guess as a slight prelude, I should mention that I understand that there's going to be some overlap between what I'm going to talk about and what Veronica talked about last week. But I think that's okay, because I'll maybe give a slightly different point of view, even though I think she mentioned some of the results that I'll be talking about today. I'll try to write big, but if I lapse, just stop me, okay? My talk today is going to be about bit threads, which is a subject I've been working on for a little while. That I gave a talk actually here during Spenta Fest about, but I'm going to start with a quick review of what bit threads are, just what you need to know to make sense of the rest of the talk, essentially, without a kind of a comprehensive overview of what they are. So, I mean, what they are is a way of understanding Ryu Takayanagi formula for holographic entanglement entropy in a certain way that I think gives us some insight into the meaning of that formula, and is useful for various purposes. And that story is what I'm going to skip, essentially, for the most part. But one of the things that bit threads do for us is to help us to understand how it is that Ryu Takayanagi formula obeys many of the basic properties that we expect entanglement entropy to obey, like subadditivity, strong subadditivity, and so on, in a sort of a much more sort of concrete way than the usual way that we understand Ryu Takayanagi. But in that story, and for example, in the talk I gave during Spenta Fest about them, and all the talks I gave over a period, I would sort of mention that there's this open problem in bit threads, which is to understand a certain property of holographic entanglement entropy, which is called MMI. And MMI is interesting. I'm going to write down what it is, but it's interesting because it's not a general property of entanglement entropy. It's a special property of holographic entanglement entropy. And so the question is sort of, what does it mean? What is it telling us about special properties of holographic states? And the hope was that bit threads might illuminate that question. And for that, we would need to understand why MMI is true in the language of bit threads. So that's the main point of my talk today, is that I'm going to use bit threads to prove MMI. MMI was previously known, so it's a new proof of an old fact. And then the question is whether the new proof illuminates things for us somehow. And I'm going to argue that it does. And in particular, what it does is it suggests a concrete structure for holographic states in which MMI becomes manifest. In this part, it will not be a proof. This part will be a proof. This part will be a suggestion, conjecture, which is suggested by this proof. But it will be a concrete structure for holographic states in which the MMI property simply becomes manifest. Okay? Okay, so in this talk, I'm going to be working in the sort of simplest framework of holographic entanglement entropy, which is classical Einstein gravity, so large N, large lambda limit, and furthermore, the static context. So static, or it's enough just to have a time reversal symmetric slice on which Ryu Takayanagi becomes a minimization problem. So this is the framework in which I'll be working today. Now, I have things to say about bit threads under the relaxation of each of these restrictions. So, but that's not going to be the subject of today's talk. So, quantum corrections to bit threads. My students and I are currently working on corrections to the bit thread story in the presence of higher derivative corrections. And something I'm working on with Veronica Hubany is a covariant version of bit threads. But in this talk, I'm just going to do the simplest case where, as you all know, Ryu Takeyanagi tells us that given a region on the boundary, and we could have some, maybe we have some black hole in the bulk or something like that, the entropy is the minimum area over surfaces in the bulk homologous to A. So in this talk, I'm going to be setting 4G Newton equal to 1. And also, it's just easier when I start talking about bell pairs. I really mean log 2 bell pairs, because there's this annoying fact that a bell pair, the entropy of each qubit is log 2 instead of 1. And so let's just forget about the log 2s. Okay. All right. So that's RT. And then what we're going to do is we're just going to have a different form of this formula where you have these things called bit threads. So a bit thread is a one-dimensional. So regardless of how many dimensions you're in, a bit thread is a one-dimensional curve in the bulk, which connects points on the boundary, a point on the boundary to another point on the boundary. And it obeys these two rules. Actually, you know what? For a few minutes here, I'm just going to put this back in because I want to make one point. So a bit thread is a curve in the bulk, and in my paper with Mike Friedman on introducing bit threads, the bit thread was an oriented curve. Now it's going to be unoriented, and if you want to know the details, I mean, there's sort of a way to go back and forth, but it just turns, it's going to be more convenient for what I'm going to do today to drop the orientation, okay? And it follows these two rules. So the first rule is that it ends only on the boundary. So it goes from one point in the bulk, one point on the boundary to another point, or it can also end on a horizon if you happen to have a horizon. So something like this is also allowed, or I guess something like this is also allowed. And the second is that the density is bounded above by 4G Newton. In other words, in other words, each thread has some thickness 4G Newton, if you want to think about it that way. And so it occupies some amount of space, okay? And so the point I want to make here is that the thickness here is microscopic. So we have these two rules that bit threads obey. And then we have a new formula which is that if you want to know the entropy of some region, you look for a configuration of threads that simply maximizes the number connecting the region to its complement or the horizon. Okay, this is going to be a macroscopic number because each thread has thickness, which is Planck scale, and so the number you're going to get is going to be like 1 over g Newton, which is n squared or c. The claim is that this number equals this number, and so there's the intuition, and then there's the official theorem. So the intuition, I mean, it's almost an obvious statement. You just can't put in any more subject to these rules. Why can't you put in any more? Because somewhere it's blocked. Somewhere there's a traffic jam. Somewhere you've put as many as you can. They are tightly packed. Where is it that they are tightly packed? Well, the first place that they're going to be tightly packed, as you start putting in more and more, is on the minimal surface. And if you think about it, it's the minimal surface homologous to A. So it automatically builds in the homology condition. And so on the minimal surface, the threads are going to be maximally tightly packed. And elsewhere, they'll be quite floppy. Okay? So the configuration of threads which achieves the maximum here is sort of locked down on the minimal surface, but away from that, it's very non-unique. Yeah.
Less than equals to 1 over 4 gen. That comes from if you integrate over the full minimal area, that should give you back the entanglement.
Yeah, I mean, these rules were chosen so that this would equal that, right? Exactly, so that then the number that you get, if what I'm saying is true, that that on the maximizing configuration, the threads are maximally packed here, then the number of them, then their density on here is saturating this bound, and then it follows that the number of them is equal to this 1 over 4 g Newton times that area. Question? Yes?
This is the term that gives you the maximum of the entropy, but there's some path integral you need to do all these configurations and. You see what I'm saying? You see, there are many other configurations of bit threads
Yes.
which would not maximize
Correct.
the number of.
Correct.
Is there any sense in which those configurations are relevant, or you only want to look at the configuration that maximizes?
Right. So indeed, Suvrat makes a very important point that I want to emphasize here, and that sometimes people sort of miss in the discussion of bit threads, because the important thing is never any single particular configuration. The important thing which represents the state, which gives you the entropies, is the collection of all possible configurations subject to these two rules. And the whole game, if all you want to do is compute the entropy of a single region and you don't care about any other aspect of the physics here, then it's fine. You just look for maximizing configuration and you're done. But many, many more interesting things come when you look at space of configuration and what freedom you have in choosing the configuration subject to certain constraints. Okay, any other questions? Yeah.
I mean, this is a very naive question, but I always wanted to know whether these of this theory. What is this stuff?
Right. I don't think it's useful to think of them as being physical objects, the way like a string is or D-brain or something like that. But what they are is, so we know from I'm only going to give a vague answer to this question. I mean, ultimately what we want to do is we want to understand, so at some deep level, how the geometry captures the state, right? And this is like, and so Ryu Takenagi is telling you something about this, and this is giving you some intermediate step in that connection between the geometry and the state. Now, it would, a fantasy would be to sort of go the other way and start with the state and its entanglement structure and all of its entanglement entropies, and then from that get some thread configuration, and from that get, a geometry. Okay, and I have some ideas about that, but that's not the subject of today's talk. But I don't think you should, and one reason you shouldn't think of them, again, as being physical objects is that no one configuration is the bit thread configuration. It's all of them, right, that you really need. Yeah. There was another question in back? Yeah.
Yeah, so in a situation where you have a horizon, let's say.
Yeah.
So is there any significance of the quantity, let's say, of the flux of the bit threads that are going to the horizon compared to those which is going through a complement, let's say?
Yeah, I mean,
there is significance to that.
I think, so this is actually, I mean, Jan and friends are thinking about this question. Actually, there's various things to say about that, and some of what I talk about will be relevant to that. But so the first thing I want to say is that that number, how many are ending on the horizon versus how many are ending elsewhere on the boundary, is not fixed.
Sure, the difference, something like that.
And so there's some freedom in how many you put on the horizon. And that number of how many, like, for example, the maximum number that go on the... Okay, so let me first say, sort of, I think at some moral level, what you want to say is that the threads that connect a point on the boundary to another point on the boundary represent entanglement, and a thread that ends on the horizon represents some mixedness. Now, it's known that in a mixed state, the question of how entangled, so if you have a mixed state of a bipartite system, and you ask, well, how much entanglement is there between the two parts? That question does not have a single well-defined answer. And so it's actually natural that there's sort of many different ways of representing entanglement between A and its complement in this thing. But there are specific answers like entanglement of purification, entanglement of distillation, this and that, and some of those might be given by some particular choices of threads. And so actually there's a story relating bit threads to entanglement of purification, and recent work that's been a conjecture about holographic entanglement of purification. And basically, I mean, the only thing I want to say, because I don't want to give a talk on that, is that that story about holographic entanglement of purification has a very natural bit thread version also. Okay. Any other questions? Yeah.
Yeah, I wanted to relate your definition with what Veronica had given in terms of flows, and that maximizes the flux, where it introduces thickness of the bit threads and all. So can we see the relation?
Yeah, so, okay, so as I said, there's the intuition and then there's the theorem. So the intuition I gave you, I think it's an almost obvious statement, I hope. I mean, sort of once you think about it a little bit. But of course, you might worry whether it's actually true. I mean, and so thankfully there's a theorem. The theorem is called max flow min cut. And what it does is it relates this quantity to the maximum flux of a vector field subject to constraints. And then what I did is I translated those constraints into the language of threads. And so if you want, there's a step in that theorem, there's a step in between, which is the flow and the vector field. And so everything I say today, you can say in the language of flows. And a flow is a vector field. I'll just say it's a vector field which is divergenceless and has a bounded norm. And I find it a little more intuitive to think about the threads, which are simply the integral curves of the flow. The way when you talk about electric and magnetic fields, you often fall back on the field lines, which is very useful. So that's what I'm doing. I'm just falling back on the field lines. Okay. And one other thing. that I want to say about the math. So let me actually write this. So in terms of the mathematical machinery backing up the basic bit thread story, as well as what I'm going to talk about today, is this subject. So there's a whole mathematical machinery here, which is the subject of convex optimization theory, which is quite a beautiful subject, mostly developed by engineers, but which has applications to geometry that I think are, to some extent remain to be explored. And I'll just give you a small taste of it, and then I'm just going to ignore the mathematical machinery and just focus on the physics. But I do want to say a couple words because it's very beautiful. So in proving a theorem like this, what you do is you express the two sides in terms of convex optimization problems. The convex optimization problem is the problem of maximizing, well, let's for concreteness say minimizing a convex function over a convex domain. And there's all, tons known about the properties of such problems and their solutions. And one of the standard tools in the theory of convex optimization is something called Lagrangian duality, which relates to such problems. And this is an example of Maxwell-Min-Cut is an example where you relate a minimization to a maximization problem, and it works in the following way, which is actually very familiar to us physicists, which is that you have some constraints and you impose those constraints using Lagrange multipliers, and then you solve for your original variables and you're left with the problem in terms of your Lagrange multipliers. Well, that's the same trick that we use to prove dualities in quantum field theories, right? You introduce some extra variables which are constrained, and then you introduce Lagrange multipliers to enforce the constraints, and then you integrate out the original variables, and you're left with a quantum field theory described in terms of the Lagrange multipliers. And so here the only difference is, well, first of all, it's classical, and second, there's inequalities. In one direction, it's kind of trivial, which is that this number is bounded above by this number. But the fact that you can achieve this number in terms of the threads is the statement that there's no other obstruction somewhere else. And that's extremely intuitive, but you never know in math. There are things that seem intuitive and they're not true. And an example in this category is that if you try to do the same thing for higher codimension, so instead of codimension 1 minimal surface, like some codimension 2 minimal surface, and then now the dual thing would be a 2 form. Anyway, there's a very natural thing that by the same logic is sort of obviously true, and it's not true. Okay? And it's not true. So there can be hidden obstructions so that the minimum on one side is not the maximum on the other side. Okay? So, so I just think it's nice that there's a theorem. Okay. But you should, but to some extent, I guess, having said that, we can now forget about that. Okay? All right. And one thing I did with Veronica a few months ago is generalize this to a Lorentzian spacetime where you have time-like a time-like vector field, and you can look at the maximum volume spatial slices versus the minimum flux of a flow. So you can play games like that using the same technology. Okay. Yeah. No, that's a separate thing from the covariant bit threads. Covariant bit threads are more complicated. And we haven't written that up yet. And yeah, that's kind of that's a whole thing in a way. But it's another example where you, to do it right, you really need this technology. Okay. So I'm ready, if you guys are, to move on. So let's just start. So it's a constraint on entanglement entropies of holographic states. Which you can write in terms of the mutual information. So. And this thing has various properties. So it's non-negative, and you can write strong subadditivity in this way. And these things are true. So these things hold for general quantum states. Okay. MMI is an inequality which doesn't. If you care, what are these letters? Monogamy of mutual information. It's not the world's best name for an inequality. I would prefer to call it superadditivity of mutual information, because that's what it is. It's saying that the mutual information between A and BC is at least the sum of the respective mutual informations. Okay, and we can write it also in terms of the entropies. Okay, and you prove it. So you prove it from the minimal surface formula from Ryu Takenagi by a cut and paste argument. You look at all the minimal surfaces that enter on the left and right hand sides, and you cut them up and glue them together again, and then you have kind of an inclusion-exclusion argument which gives you the inequality. If you've seen the proof of SSA based on Ryu Takenagi, it's the same thing, just more complicated, and it gives essentially no insight into why this thing is true or what it means. As I said, it doesn't hold in general quantum states, and I'll give you an example in a second, but let me first do something to help us understand it. So I'm going to define a quantity which is the generalization of mutual information, the tripartite information, and this thing has a funny name. It's called minus I3. Some people define I3, which is defined as the negative of minus I3, but minus I3 is really a much more natural quantity, so you should never talk about I3, you should only talk about minus I3. So it's just the difference here. Okay, and it's manifestly symmetric under permutations of these three, but it's actually a really, really nice quantity. And so to illustrate that, let's purify the system, okay? So let's purify ABC into ABCD. So that, for example, here, if you want to purify this system, let's say we had ABC, then just add the other boundary upon the completion, if you want going to the thermal field double, and then that's a nice purification, which is holographic. It's important, when you purify it, it's important that you purify it not just in some abstract way, but that you purify it into a state which is also holographic. right? Because we're going to apply, Ryu Takanagi and so on to the purified state. So, but we know that we can do that, so that's nice. Then, when you write this down, you see that this thing becomes S of D. S of AB is equal to S of CD. S of AC is equal to S of BD. And S of BC is equal to S of AD. And by the time you're done, the thing is fully permutation symmetric under all four. So I'm not even going to write the arguments. Is S4 symmetric? Okay. Without loss of generality. Thanks for asking. Okay, so it's fully symmetric. It's only sensitive to fully four-party entanglement. So what I mean by that is if your state looks like this, so remember, by definition, it's pure. If it happens to be a product like this, in which any one of the four is separate from the rest, or any two are separate from the other two, then I3, then minus I3 is 0. Yeah.
But in general, you might have a separable state, which is a sum over, over product states, and that is not something we call genuine four-party entanglement, right? That's a classical mixture of.
My state is pure. So, yeah, for example.
Sorry, I'm a bit confused. Sorry, let me. Psi ABCD is a pure state.
Yeah.
Okay, I get it. So, yeah, okay.
So in these two cases, and obviously permutations of them, you get this. And that it's just a simple, just plug and chug, and you see that it's true. Right. No, so certainly not. I wouldn't say if it's a non-trivial linear combination, that's true. But if it's a tensor product of such states, or if you have a part, like if there's some part of A, B, C, and D, which has this structure, that part will not contribute to minus I3. So only the parts which have a fully four-party entangled state will contribute to minus I3. So in general, this thing can be positive or negative or zero. And let me give examples. So if you, the simplest example where it's positive, which is basically the simplest fully four-party entangled state, you can possibly write down, which is just a four-party GHZ state, then you calculate it, and you get 1. Sorry. That was the negative case. On the other hand, and let's see, if we... You can see why, because in this mutual information here, so let's trace out D. If you trace out D, you get a classical state, which is a mixture of 0, 0, 0 and 1, 1, 1. And so between A and BC, there's 1 unit of correlation. So you get 1 here. Between A and B, so A, B, and C are perfectly correlated classically in that state. So this is 1, and this is 1. Okay, so this minus this is minus 1. On the other hand, you can get a positive value, and the simplest example where you get a positive value is one of these perfect tensors. And a perfect tensor state is one where every subsystem is maximally mixed. So perfect tensor means that all of these guys are equal, and they're all equal to a half of all of the two-party guys. Okay, and then you plug it into the formula, and you find, and since these are positive quantities, you find that this, so that implies that this is positive. And if you want to, so I didn't write down a formula, but these things exist. The simplest example is there's this thing called the 4-qubit. These things are used in the theory of error correcting codes. So the simplest example is on 4 qubits, it turns out. They don't exist on 4 qubits, you can show. Perfect tensors don't exist on 4 qubits. So this shows up, for example, like in the happy code. Yeah.
My inequality you wrote before.
Yeah.
So this kind of inequality is saturated by some entanglement measures. In particular, if you define entanglement, in some more, so the mutual information is relative entropy of the state with the product state.
Mm-hmm.
But if you try to define entanglement as distance to the nearest separable state, which may not be the product state, then sometimes I'm not sure. Yeah, I'm not sure if you define it with relative entropy, it works. But I think you can find measures that do satisfy these kinds of inequalities. So in fact, correct me if I'm wrong, I think in the quantum information literature, this is what people usually call monogamy of entanglement, an inequality of this kind. Is that
right?
So is this somehow a statement that the product state is the nearest separable state in holographic theories? Something like that?
Right. So, so first of all, just to give the background to your question, the name. So this is monogamy and mutual information, and as Suvrat said, so the term monogamy in the quantum information literature is applied to measures of entanglement which obey an inequality of this form, where this is not the mutual information but some other measure of entanglement, and it's closely related to the monogamy of entanglement property. So then, yeah, the question becomes, why? For holographic states, does the mutual information obey this property, which normally it doesn't? So you wanted to say that for holographic states, somehow the mutual information is the distance in some sense?
If you define entanglement as distance from the state you are to a separable state, that would not be mutual information because mutual information is distance to product state.
Right.
But maybe somehow for holographic theories, nearest separable state is product state.
The nearest separable state is a product state. I would need to think about that. It's a good question. Yeah. I'm going to give a different, well, maybe it's not different, maybe it's the same, I don't know, interpretation of this. So actually, I'm going to give two possible interpretation. So the first thing is that if sort of very crudely you take these as the prototypical types of four-party states, and in fact the world is more complicated than that, but if we take these as sort of the prototypical kinds of building blocks, then this inequality is telling us, which I can now write in this form, that perfect tensor type entanglement dominates over GHZ type entanglement. Roughly speaking, it seems to suggest that. Okay, and I'm going to try to be more, I'm going to make a stronger statement later in the talk. So if you had a state which was just a bunch of perfect tensors and a bunch of GHZs, and it was holographic, you would have to have had more perfect tensors than GHZs. It was negative, right? Okay, so this is only supposed to be at best some type of heuristic statement. Yeah. It's a function of the dimensions. Yeah, I assume that question is certainly answerable. Although not necessarily in real time, but I mean, it's going to be some number times the log of the. Yeah, I mean, there's going to be some statement about, especially if they have different dimensions, some difference between them or something like that. Yeah, everything here is linear. Yeah, the log of the dimension, yeah. Yeah. Yeah, it obeys MMI. So if you just plug in the page curve, if you just say, okay, random pure state in a high dimensional joint Hilbert space, then just plug in the entropies you get from the page curve, they obey this. Yeah. Right, it takes atypical states to violate it, but I mean, this argument has never been that impressive to me because it's not like the entropies in holographic states are given by the page curve. So they aren't random states. We already know they're special states. So we already know they're atypical in that sense. So it doesn't exactly solve the problem. Okay. So I want to do a quick interlude on the space of entropies, which is just a handy. So when you tensor product systems together, and tensor product their state, then the entropies are additive. So the entropies live in a kind of a vector space under the operation of tensoring states. And so, but at the same time, they obey inequalities, like the entropies are positive, the mutual information is positive, and so on. And so those inequalities cut out those are linear inequalities, and what they leave behind is some cone in the space of entropies, which is the entropy cone. And there's different entropy cones. There's the entropy cone of states that, general quantum states, and then there's the holographic entropy cone. It'll be handy for us to talk about so coordinates on this space. The situation gets much more interesting when you go beyond 4, and I'm not going to do that because that's a different topic that we don't really understand very well. I mean, we understand some things about it, but I'm going to stop at 4. So, and basically what I want to know is how many variables we have. So here we have this. And so there's one independent entropy. For n equals 3, we have like S of BC equals S of A, etc. And so we have 3 independent entropies. And a nice set of coordinates are the 3 mutual informations. So, you can use as coordinates on this cone either S of A, S of B, S of C. That's 3 good coordinates. Another set of coordinates which are linearly related are these. And these are nice because they encode. So if you basically take these 3 to be positive or non-negative, then you get a valid set of entropies. So you don't need to introduce any other inequalities. For 4, what do we have? Well, so we have these four. And then independently, we have these two-party entropies. But of course, this is equal to S of BC, S of CD, etc. And so the total is 7. It's always 2 to the n minus 1 minus 1, you can show. And a nice set of coordinates is, again, the two-party mutual informations, etc. So there are 6 of these. And then the last thing is minus I3. And what's nice about this set of 7 numbers is once you guarantee that all of these are non-negative, so as long as all of these are non-negative, that guarantees that all properties are obeyed. So that immediately implies this and this and this. So that's why they're nice coordinates, that's all. Okay? You don't have to check that they obey some inequality to make sure they make a valid set of entropies as long as each individual coordinate is non-negative. Okay? So that's handy. Okay. Yeah. Sorry, so this last statement was for the holographic cone.
Okay.
Yeah.
Traffic case minus I3 is always positive.
Yeah.
Okay.
Yeah, and so the only one that's left to check is this, but basically it's a very straightforward algebra that subadditivity plus MMI implies strong subadditivity. So you don't need to check this one for any, and all permutations of it. Oh, what? Say it again. No, these two do not imply this. Any other questions before I erase this? Okay, so what's left to do is to prove that minus I3 is non-negative. And based on bit threads. So you need some machinery, and in the proof, depending on what you're trying to prove, you need to know some facts about possible thread configurations. And it turns out that for each inequality you want to prove, there's some new you need. And so, for example, if you want to prove subadditivity, it kind of falls in your lap. If you want to prove strong subadditivity, you need this so-called nesting property, which says that if you have two regions A and B, there exists a thread configuration which maximizes the number of threads coming out of A and A union B. Not the number coming out of A and the number coming out of B. That doesn't exist in general, but the number coming out of A and the number coming out of A and B, A union B. In other words, there's a single thread configuration which simultaneously calculates for you S of A and S of AB. And this is called the nesting property, and it's used in the proof of strong subadditivity. The nesting property is not powerful enough to prove MMI, you can show. And so there's some other fact about threads, which we finally found in the literature on flows on networks. So there's a large literature on flows on networks. And in particular, what you have to do is you have to kind of broaden your perspective a little bit and stop thinking about individual flows and start thinking about, individual thread configurations, and think about sort of thread configurations that are compatible with each other. So what that means is you have some thread configuration which does more than one job at the same time. And those things are called, in the network flow literature, they're called multi-commodity flows. And they were intensively studied, especially like in the 80s, by Soviet mathematicians who were interested in basically optimizing the centrally planned economy. So you have a situation like this, like you have some railroad network, each link has a certain capacity in terms of how many trains it can take, and you don't just want to solve some max flow problem where you want to maximize like the number of potatoes you ship from here to there, but on the same network, you need to maximize the number of potatoes you ship from here to there and the amount of coal you ship from some other place to some other place and the amount of cabbages you... And so on the same rail network, you need to maximize all of these flows, right? And so that's what they were studying. They proved all these theorems about them. And so we took one of those theorems, which I'll write down in a second. But the challenge was that, of course, the theorem had been proven in the network context, which is a discrete setting, and we want to work in the setting of Riemannian manifolds. And so we had to find a proof of this theorem. And so that's what we did, and that's definitely the hardest part of this whole thing, and I'm just going to entirely skip it. But it's actually a very beautiful proof that uses this Lagrangian duality business and so on. It looks completely different from the network proof. So what is this statement I keep talking about? So given n boundary regions, there exists a thread configuration, which if you want, I could have said there exists a flow, with the following miraculous property that for each individual, so I should call these regions, sorry, A1, A2, etc. For each individual region, it maximizes the number. So the number of threads from AI or connecting to the complement, it is the maximum you could possibly put, which by definition is, which I'm using the notation S of AI. Okay? So in other words, there's one thread configuration which calculates for you S of A1, S of A2, S of A3, S of A4, etc. Okay? This is an amazing fact. This is not something which is obvious. Okay? So let me just do some examples. So this is, n equals 2 is a completely trivial statement. It's actually pretty much content-free. It's just saying there exists, because you already know that for any thread configuration, the number from A to B is the same as the number from B to A, and so just saying there exists one which maximizes that. It's much more interesting when you have more than two. And it's even more interesting when you get to 4. So let me just... So there's some thread configuration which includes threads from A to B, from A to C, and from B to C, which is such, so let me call this number NAB, NAC, and NBC. And now my claim is that this thread configuration is such that S of A is NAB plus NAC, etc. And now, for example, let's do the following thing, which will help our intuition a lot. Let's calculate a mutual information since we have this data. Of course, this is obviously the same as this. And so what do you get? Well, it's very simple. You get this. So what is this number? It's just twice the mutual information between A and B. And these numbers are, so knowing all three mutual informations, as I said before, is the same as knowing all of the entropies. That's all the information there is in the entropies of this three-party system. And so that means that these numbers, these three numbers, are fixed. That doesn't mean the thread I didn't say this thread configuration is unique, the one that does this job. It's not. There's a lot of floppiness, but the number from A to B is fixed. The number from B to C is fixed, and so on. Okay? So this is great because it's such a simple formula which directly relates the number of threads connecting A and B to the mutual information. Okay? It gets more interesting when we go to 4, because there's going to be a twist, because we already know that the mutual informations are not the full story. We already know there's only 6 of those, and there's a 7th number, which is minus I3. But what kind of thread configurations are we going to have? Well, all they're going to do is connect, A to B, A to C, and so on. That's all they can do, right? And it's in that separation between the numbers that are the number of threads connecting, so the sort of the bipartite thing, and the entropies, it's in that space in between that minus I3 pops up. Okay, so let's do the n equals 4 case. Yeah.
Like here you only got in terms of NAB, means if you consider higher ends, there'll be other independent factors. Means these numbers are fixed, but what are those numbers independently? They depend on n, right?
Wait, say it again?
Means how many independent numbers you have. Once you fix those, all our others are fixed, but that depends on n, means how many.
Yeah, the number
independent that you need to fix it.
The number of independent numbers, the dimensionality of this entropy cone is 2 to the n minus 1 minus 1.
Thank you.
Okay, so here we get, I'm not going to draw it in this way, but maybe I'll draw it like this, as a tetrahedron. And so we get, NAB, etc., such that S of A is NAB. It's just the total number, the sum of these numbers. So plus NAC, plus NAD, etc. But I've erased my formula for minus I3, but it involved not just S of A, S of B, S of C, and S of D, but also the two-party entropies. And so the question now is, well, great, you've got this thread configuration, please tell me S of AB, because that enters into the formula. Well, we go back to this theorem, and it doesn't mention two-party things. It only mentions the one-party things. It doesn't tell, this thread configuration doesn't tell us S of AB. So you might think you're stuck, but it tells you something about S of AB because it's a valid thread configuration, so it bounds S of AB below. So it doesn't tell you what S of AB is, but it tells you S of AB has to be at least the number of threads connecting AB to CD in this thread configuration. And what is that number? Well, that's this number plus this number plus this number plus this number. So we get an inequality. And now you just plug and chug. So the formula had these four numbers. It had these three numbers, each of which has four terms, minus these four numbers, each of which has three terms. And you can see it's the same terms. And so you get from this inequality this, okay? So that's the proof of monogamy. By the way, I meant to say something, which is that along the way here, I proved subadditivity because these ends cannot be negative. I mean, there's many ways to use bit threads to prove subadditivity. This is definitely not the easiest to use this whole machinery and everything, but it fits in. Yeah. Yeah. Yeah, I mean, minus I3 is the sum of the, with AC and AD. So then I add up 12 numbers, but with an inequality. And here I add up 12 numbers. It's the same 12 numbers. Okay? So this inequality comes from this. Okay? Now, at first sight, so in particular, if you compute this, all you get, if you go through the same exercise, all you get is this inequality. So the number here may be larger than the mutual information. This seems a little bit surprising, right? Because you might have thought that this number is, each of these is representing some bell pair, morally speaking, and so the number of them is half the mutual information. But here I'm telling you the number of them can be more. So let me look at an example to kind of clarify this situation. So let's just do a simple graph where the capacity is 1 on each, and there's no restriction on the vertex. And let's look at the thread configurations that satisfy this theorem, and you find that there are 3 of them. So one of them looks like this. Another one looks like this. And the third one looks like this. Okay, so because S of A, S of B, S of C, and S of D are all 1, S of AB is 2, and so on. So here each of these is telling us correctly the entropy of each individual thing. But if you look at this one, for example, so here, these are all 0. So what is this thread doing? Well, the point is that there is some freedom in choosing these ends, which we did not have in this case. And the freedom in choosing the ends, how much freedom is there in choosing the ends? It is minus I3. Okay? So minus I3 is the number of threads for which you have the freedom to reconnect them in this way. Okay? The minimum number, so I can turn this into an equality by saying that overall, the thread configurations obeying this theorem, the one with the smallest NAB tells you this, and there's a factor of 2. Okay. All right. So the threads which there's sort of essential threads connecting A to B, and the number of those is the mutual information. And then there's the ones that can switch around with CD threads, and the number of those is minus I3. Okay? Yeah.
NAB.
Mm-hmm.
Then are you just saying the minimum number? I mean, why is it equal to minimum number? I mean, there, yeah, go ahead. This is something there. Yeah.
So what I meant here is look at all of the thread configurations which are of this form. The minimum among those of NAB is 1/2 the mutual information. Okay? Yes?
So,
Oh, sorry.
Just saying, because if I just wanted to compute IAB, I wouldn't care about the other regions, and I would try to compute SAB as per your threads, etc., etc. Will that number somehow agree with the minimum? What does minimum NAB mean? Does that mean I keep track of these 4 regions and then?
Right. So here I have A, B, C, and D.
Yeah.
And then, so that imposes, then applying the theorem, it's different from if I applied the theorem to just something where I just had A, B, and C. So in other words, if you take a thread configuration here, and then you simply merge C and D, consider them to be a single region, what you get is not necessarily an n equals 3 thread configuration. But some of them are. Yeah.
So other than mutual information and tripartite information, if you look at higher order measures of multipartite entanglement, then do these kind of considerations impose additional constraints on the holographic states? Like what kind of holographic states you can have?
You mean n larger than 4?
Yes.
So that's, so there are known constraints for n larger than 4.
Which do not follow from...
Which do not follow, yeah, there are no new constraints. Yes, that's right. First of all, we don't really know what those are. I mean, we know some of them, but we don't know whether we know the complete list or not. So we basically don't know what the holographic entropy cone looks like for n greater than 4. And we don't know how bit threads, fit into that story. I mean, in terms of open problems, I think understanding the n greater than 4 holographic entropy cone, either from the point of view of minimal surfaces or from the point of view of bit threads, is very interesting and not really. I mean, some things are known, but yeah. Yeah.
So this theorem about multi-commodity flows, is it for Riemannian manifolds or Lorentzian manifolds or both?
Riemannian manifolds.
Not Lorentzian.
Yeah, I mean, so we haven't gotten around to trying to generalize that to the covariant bit threads and so on. We haven't done that yet.
So maybe I just want to postpone all questions to.
Okay.
So we can.
Okay. All right. Because we need a picture and we need to eat lunch. So I just had section 4, and I'll do it really fast. This picture suggests, it doesn't prove, but that a particular structure for the state, maybe I'll just say it in words. Let's start with in the n equals 2 case, of course, by definition, because I'm assuming you purified your state, what do you have? You just have bipartite entanglement, and the amount of that is S of A. Okay, big deal. Now, this picture to me suggests that when n is 3, then all you have is bipartite entanglement, so that the state on ABC admits a decomposition. So A admits a decomposition into a part of A which is going to be entangled with B, and a part which is going to be entangled with C, and similarly for B and C, such that the part of A which is entangled with B union the part of B which is entangled with A is just a bipartite pure state. Now, here we have to be a little bit careful so that we're not making an obviously false statement. This decomposition is not a spatial decomposition, despite what this picture might suggest, because we have to remember the freedom in the thread configuration. There are no well-defined points where this particular thread ends and this particular thread ends. We can move them around at will on the boundary. It's just the number which is determined. Okay, these three numbers are determined. So this decomposition is not a spatial decomposition. Okay? This picture suggests a similar decomposition. So first of all, I mean, I think already this is a very strong statement. Would be very interesting to try to prove it or disprove it. Another thing I should say is I'm working only at large n. So this thing would be true sort of at leading order in large n. Okay? In a holographic state of a holographic theory, there's a decomposition of the A Hilbert space, of the B Hilbert space, and of the C Hilbert space, and in a given state. So I have a fixed state, right? I mean, this decomposition is going to depend on the state, okay? But the state has the form that part of the A Hilbert space and part of the B Hilbert space are together in a pure state. In other words, to say it a different way, there's no GHZ or W type three-party entanglement. Or to say it slightly more precisely, the GHZ and W type part of the wave function is subleading in 1 over n. And the leading order part is just only bipartite entanglement. Okay, if it's true, it's a very, very strong constraint on the nature of holographic states. Okay? What is the four-party generalization? It's similar, but of course, yeah. Let me write down the four-party thing, and then, so the four-party thing is that, of course, you simply have the part of A which is entangled with B, the part with C, and the part with D. So you have these, but you also have a part which is going to be doing the perfect tensor part of the wave function. So you have four parts, similarly for these, and similarly for D, etc. And so you just have bipartite entanglement. So these things, and perfect tensor type entanglement. So that is in, so in other words, A, B, is equal to a perfect tensor. A check on this picture is that if you assume that it's true for n equals 4, and then you merge C and D, consider CD to be a single system, you can take it, then it reduces to the n equals 3 picture, which is obvious for the bipartite part. But for the perfect tensor, it's a true fact that if you take a perfect tensor and you merge two of the parties, you can do a unitary on the Hilbert space for CD such that it admits a decomposition of this type on the remaining three parties. Not in terms of the original C and D Hilbert spaces, you need to do a unitary on CD. Okay? So that's a check on that this story is at least consistent within itself. So this is a very strong conjecture, maybe completely false. But I think it's very interesting to ask how we would know whether it's true or false. It's not implied by the bit thread picture, but it's suggested by the bit thread picture. So I think it's worth kind of thinking about. Multiple times I've had conversations with people who've told me it's obviously false, and they've told me why, and it hasn't been true, what they've said. So it's still alive as far as I know, but I think it's worth thinking about some more. And now I'm finally done. Thank you. I learned from my advisor how to give talks, right? Is there time for questions, or we got to go take a picture?
Few quick questions.
You can tell us later, but I didn't even understand quite the basis of the conjecture in the string picture. I understand that of all the strings leaving A, some are going, one place or another. But are you saying, therefore, that of all the entanglement A has, some comes from B, some comes from B? That seems to be what's said.
Yeah, that the entanglement of A with its complement, we know the amount of that is S of A by definition, but that it actually decomposes into some amount which is just with B and some amount which is just with C. I mean, in a general quantum state, this is not true at all. It seems to look like that.
Is there a bit thread picture in de Sitter space where the bit threads start and end at the space-like boundary or the horizon, the cosmological?
Yeah, so for that you need covariant bit threads, and I haven't quite been able to get it to work, but I may not be thinking about it right. So I can tell you about covariant bit threads later. And I mean, you really need, obviously you really need the covariant picture there.
Thank you.
So if this is a statement which is valid at large n, where most of the entanglement comes from UV degrees of freedom near the endpoints of these, near the boundaries of these regions, if you think about some spatial regions, is it not a fairly obvious statement from that point of view?
Well, but that's only, I mean, that's the boring part. I mean, I agree with you that, there you have a different parameter, which is the UV cutoff. And the leading term as a function of the UV cutoff, indeed, is this entanglement between nearby points on opposite sides of the entangling surface. But that's not, and so yes, for the leading part, the area law part and all the divergent parts of the entanglement entropy in terms of the UV cutoff, it's kind of obviously true. But of course, that's not the interesting part anyway. The interesting part is like the part that's deep in the bulk and so on, right?
Right, but that's...
I mean,
confused about this, the statement that it's only the leading term, and so you're
in 1 over n.
In 1 over n, so
yeah, not in terms of the UV cutoff.
So it's including the finite pieces.
Yeah.
Okay.
Yeah, that's the interesting
that's where the
part.
It's to get that right.
What?
That's where the issue is to get that part.
Yeah. The UV divergent part is kind of boring. Yeah.
Finite parts. Is I3 in a generic conformal field theory?
Is negative. Well, no, that actually depends on your configuration. You can make it 0 or you can make it negative, depending on how what you choose for A, B, and C.
I see.
Yeah. I mean, it's pretty easy to come up with either way.
But in holographic theory, you're saying it's always negative.
No. Oh. Sorry, I misunderstood. I thought you were talking about a holographic theory. Sorry.
No, asking in a conformal field theory.
Sorry. In non-holographic conformal field theories, it can take either sign.
I see.
That's right. And even in non-conformal field, so free fermions, free massive fermions, you know it, and it can take either sign, depending on your arrangement of things. Yeah. So that implies in particular that when holographically it's 0 and you take into account the 1 over n corrections, those can take either sign. It's only the leading order in 1 over n part that satisfies this MMI property. Because the bulk fields don't have to satisfy this geometric constraints. So the quantum part does not have to satisfy MMI. So I think Suvrat's been waiting.
Okay. Tell me later, but why isn't your conjecture obviously wrong? Because the number of strings going from A to B cares about also whether you have the region C or not. You know, if you were having 3 regions, then the number, as you were saying, because you have some constraint in the center, etc., the number of strings from A to B would care about whether you're looking at A, B, and C or just A and B together.
No, you're not allowed to just look at AB because I'm assuming it's pure. So if you have A and B, I mean, either AB is pure, and then you're back to the n equals 2 case, or it's not, in which case you have to purify it and include C. Yeah, of course, it's up to you whether the complement you call C or you call CD or CDE and so on. So all of those, there's a consistency issue, but yeah.
Asking my question, I'll call the session to a close and we can talk later. So all of us, please join us for the photograph outside.